Hi math friends, today we're looking at section 8.2, function rules. We're going to be looking at four different terms here: sequence, term, arithmetic sequence, and geometric sequence. First we're going to look at sequences. We're going to focus on arithmetic sequence. An arithmetic sequence exists when your changes in x are always constant and your changes in y are constant. Let's look at this first example here. Our change in x as we increase is plus 1, from 2 to 3 is plus 1, from 3 to 4 again is plus 1, from 4 to 5 is plus 1. Let's look at our y values now. From 12 to 15, that increases by 3. From 15 to 18 is a plus 3 again. From 18 to 21, that's another plus 3. And from 21 to 24 is another plus 3. Since all of these changes, your change in x is the same. Another word that we use is constant. Your change in x is always constant. Our change in y is also constant. That tells us that this sequence is arithmetic. On these next two examples, I want us to look at these two charts and ask, is this an arithmetic sequence? For the first one, let's look at our x's. We go from 0 to 1, which is plus 1. 1 to 2, which is plus 1. And 2 to 3, which is plus 1. Those plus 1s are constant, so we're led to believe this might be an arithmetic sequence. Let's check out the y values though. 5 to 10 is plus 5. 10 to 17 is plus 7. And 17 to 20 is plus 3. Plus 5, plus 7, and plus 3 are not all the same. They're not constant. So we would say not an arithmetic sequence. This one up here is not arithmetic. Looking at the second one, let's see if this one is. From 9 to 10 is a change of plus 1. 10 to 11 is another plus 1. 11 to 12 is another plus 1. So our x's are constant. Let's look at our y values now. 100 to 110 is plus 10. 110 to 120 is also plus 10. And 120 to 130 and 120 to 130 is also plus 10. Since all of these are constant, and now your y's are constant, plus 10, plus 10, plus 10, we know that this is arithmetic. So we can say yes, that is arithmetic. Now we're going to discuss what makes up a geometric sequence. It's still a sequence, there's still a pattern to it, but the pattern is a little bit different. Let's look at this one. From 1 to 2, our change is plus 1. From 2 to 3, your change is also plus 1. From 3 to 4, you have a plus 1 change. From 4 to 5, you have another plus 1 change. So that's starting to look like this, kind of the same as an arithmetic sequence. Let's check out the y values though. 5 to 10 is plus 5. 10 to 20 is plus 10. 20 to 40 is plus 20. 40 to 80 is plus 40. These values are all different, so we know that that's not an arithmetic sequence. What I want us to notice though is that from plus 5 to plus 10, that's a difference of multiplying by 2. From plus 10 to plus 20, again, you're multiplying by 2. And finally, from plus 20 to plus 40, you're multiplying by 2. When these changes are constant because of multiplication, that means that you have a geometric sequence. We're going to focus on the arithmetic sequence though. I just wanted you to know what a geometric sequence is. In this chapter, you're going to be asked to find patterns and look at charts to find what a missing value will be. What is the fifth term in this chart? Well, let's see. For our x values, let's see if we have a sequence first. 0 to 1 is plus 1. 1 to 2 is plus 1. 2 to 3, plus 1 again. And 3 to 4, plus 1 again. Now let's check out our y's. 2 to 4, plus 2. 4 to 6, plus 2. 6 to 8 is another plus 2. Since this change is constant and this change is constant, we know that we have an arithmetic sequence. We know that this is arithmetic. What would our last term be if this is constant? Plus 2, plus 2, plus 2. 8 plus 2 would be 10. We're asked to find the fifth term. I want us to think about this. Our first term is always all the way on the left here, or all the way at the top of a chart. So first term, second term, third term, fourth term, fifth term. Our fifth term is 4 for your x value and 10 for your y value. Let's check out a word problem that deals with arithmetic sequences. The table shows the number of snowballs Maya can make based on the number of minutes. Write a function rule to find the number of snowballs she can make in x minutes. Here's our table. What this reads is our number of minutes, which is x, 1, 2, 3, and then our unknown, x, and the number of snowballs, 5, 7, 9, and the unknown. First we should ask ourselves, is this arithmetic or geometric? So let's look at our number of snowballs. From 5 to 7, that's plus 2. From 7 to 9, that's plus 2. So we know that since we're adding the same number to increase our value, that's an arithmetic sequence. This helps us out a lot. We know that we have to multiply our number of minutes by 2 and then maybe do something else. We know that times 2 is going to be part of our rule. We're just not quite sure what else to do here though. Let's use some guess and check. To get from 1 to 5, because remember we have 1 minute for 5 snowballs, 1 times 2 plus something will equal 5. Well, 1 times 2 is 2, plus this something equals 5. 2 plus what equals 5? If we're not sure, we can use a variable there and use the subtraction property of equality to help us solve for that. Subtract 2 from each side, x equals 3 here. So it looks like our rule might be something about times 2 and plus 3. And we can use x for the number of minutes here. So we'll have x times 2 plus 3. Another way to write x times 2 is 2x plus 3. Let's see if this works for everything else. So we have 2 minutes times 2. We plugged in 2 for x here, plus 3. 2 times 2 is 4, plus 3 is 7. And if we look back at our chart, we have 2 minutes, 7 snowballs. That one checks out. That gets a check mark. Our next one is 3 minutes to get 9 snowballs. So we're going to plug in 3 for the number of minutes. Then we have 2 times 3 is 6. 6 plus 3 is 9. Does that check out? 3 minutes, 9 snowballs. 3 minutes, 9 snowballs. That checks out. So this is our rule. 2x plus 3. Please follow along closely in your notes for this one. We're going to look at how to find a function rule for this set of data. We have our x values and our y values, and we want to find, if we used a function machine, what would that function rule be? So we're going to be looking at that together right now. First, let's see if this is arithmetic. 5 to 6 is plus 1, 6 to 7 is plus 1, then we have plus 1 and plus 1 again. We're also going to look at our y's. From 16 to 19 is plus 3. From 19 to 22 is plus 3. From 22 to 25 is plus 3. From 25 to 28 is also plus 3. So we know this is arithmetic. This plus 3 tells us that we're going to multiply our input by 3. So we should write that down first for part of our rule. We're going to be multiplying the input by 3, but then we might do something else. Let's see, 5 times 3 is 15. 15, but we need 16. What should we do to get to 16 then? We should add 1. 15 plus 1 is 16. Let's see if this rule works for the rest of our inputs. 6 times 3 is 18. Let's add 1 to that, just like we did with our 5. 18 plus 1 is 19. So 6 to 19, that one worked. Let's try 7. 7 times 3 is 21. 21 plus 1 is 22. Let's try 8 now in our heads. 8 times 3 is 24. 24 plus 1 is 25. Okay, I'm starting to become convinced. Let's just check just to make sure. 9 times 3 is 27. 27 plus 1 is 28. So our rule needs to be multiplied by 3, then add 1. Let's write that in on the function machine over here.